Good day, everyone. Today, we are going to discuss about how to write a simple arithmetic program for 8051 microcontroller and simulate it using Keil software. So, we'll be basically discussing 8 different programs. That is 8-bit addition, 8-bit subtraction, 8-bit multiplication, and 8-bit division. In addition to that, we'll do 16-bit multiplication, uh, division, addition, and subtraction. So totally 8 different programs we'll be doing. So since this is the first video for this 8051 microcontroller, what I'll do is I'll just start with the basics of how to start with the Keil software. So we'll directly get into the Keil software. So I'll close it and I'll open it again. So Keil uVision 5, this is a open end software. You can download it from the Keil website, and it's restricted to 2 kilobytes of program memory that you can run. So that is the restriction that it has. In case if you want to have a larger program to be run in this software, you are supposed to buy the original version, the full version of this software. So so the blank I mean the Keil software opens like this, and in case if you are finding out something over here, you can always close the project like this by clicking project, close project. Then you can click project, new uVision project, you can click. So you just specify the path. So I'll specify the path according to my convenience. So I'll type a name, like whatever the name that you want you can type. So I'll type the first part of my name and click save. You will get a window like this. So you will get software packs, so you can change it to legacy devices. So this happens only with Keil uVision 5. In case of Keil uVision 4, you'll not get this kind of an option. So you'll directly get into this component browser. So since Keil uVision 5 has loaded many other devices, the recent devices that comes in under the software packs. So but 8051 comes under the legacy devices. So we'll have to get into this legacy device database. So click on this legacy device database and go to NXP. So in NXP, we'll be checking for P89V51RD2. So P89V51RD2 is the microcontroller that we are going to use in the lab also. So I have chosen this P89V51RD2. So click OK, and it will prompt a message like copy startup.ta51 to project folder and add files to project. Click yes. So in case I have created already the same project, so it is asking for whether to overwrite it or not. So you can click yes. So now it has been overwritten. So you'll see this project with the name PON. So the name, whatever the name that you are giving, will appear here. And in target 1, you'll have the source group, and in the source group, you'll have this startup.a51. So this happens to be the base file. So this you are not supposed to edit it. So you can close this one, but it should appear in this source group. Now we will directly go for writing the program. So first program is addition of two 8-bit numbers. So I'll assume that I'll put two 8-bit numbers in a register and then I'll add it. So first instruction that I'll type is mov a comma hash 05h. So in this case, mov is move instruction, a is accumulator, comma hash represents whatever the things that I am going to write after the hash is going to be a number, and h represents the hexadecimal. So in case if you are not writing this hash, 05 will be taken as an address, and from that address the data will be moved into the accumulator. In case if you are not writing this hexadecimal, your Keil compiler will assume this number as a decimal number and it will convert it into its equivalent hexadecimal. So whatever the number that you are giving will be converted into a different hexadecimal number. So to avoid those things, we'll be writing as MOVA comma hash 05H. So 5 I am moving to the accumulator. Next MOV B comma hash 03H. So again in the B register I am moving the content 03H. So then I'll add both the registers, add A comma B. So in this instruction A and B is summed up and the result is stored in the accumulator. In 8051 this thing, one thing you'll have to keep it in mind. So all the arithmetic and logic operation has to be directed towards the accumulator. You can't use any other register. Add B comma A is not possible. Add A R0 comma B is not possible. So all the result has to end with the accumulator. That has to be kept in mind. So this is the end of the program, and here I'll write a instruction like L colon is jump L and end. So this end represents the end of the program. So S jump is short jump. So this L is a label and that L I am connecting over here. So whenever the program completes this operation, it comes and stays inside this line itself. If you're not writing this instruction, what will happen is your controller will try to execute the garbage value that is available after this add instruction. So it will give an error like access violation. So to avoid that kind of an error, we are writing this L is jump L. Okay. So after writing this program, we'll save it into the folder. So here I'll put a name as add.asm. So we are writing the program in assembly language, so this ASM is significant. So if you are missing this ASM, your program may not work. So you can see after I have saved the content, the values, the program that I have written, you can see the color that has changed. So instructions appears in blue while registers appears in green and the numbers appears in red color, while the label here that appears in black color. So after saving this, you can go for connecting this add.asm inside the source group. So right click in the source group and click add and click on this ASM. So then only you'll see the files that is available inside the folder. So click add and click add.asm and add. So it will come here. So this add.asm has been connected to the source group now. So after connecting it, you click on this translate. So you should get 0 error and 0 warning. So this translate is helpful in checking where the error is. In case of error in the sense syntax error. Say like if I instead of add I am writing instruction like ADDA. So you can see when I'm writing ADDA, the color of the instruction has changed to black, which means that it is not accepted as a instruction. So I'll save and translate. Now you can see in the number 3 line, so there is a syntax error. The line number has been specified over here. In the line number 3, you have a syntax error. So you can identify the error in this fashion. I'll delete it, save, translate. So now you can see 0 error, 0 warning. Then build and rebuild. Directly you can click on this button also. See, in the same error I'm making, ADDA, I'm pressing this button. So you can see it says that target not created. But translate will give you the option of checking out in which line you have the error. So now we have translated, build and rebuild. Then you press this startup debug session and click OK. So now here you can see the registers available R0, R1, R2, R3 up to R7, and then AB. So we are using this AB only. We haven't used this R0 to R7 registers. So let us go step by step. Here you can directly run also. So totally it will run the program and it will give the output. So we are not going to do that. We are going for step by step operation. So first click the this step button. So mov a comma 5 has executed and the accumulator has 5, and then mov b comma has 03, so b register has 03. Then add ab, 5 and 3 is added and the result is 8. So this is the way in which you program the addition. So in the same program you can go for doing for subtraction. SUBB means subtract with borrow. Actually in case if we want to carry over the borrow from the previous subtraction, then this instruction is helpful. So but you don't have subtract without borrow. Subtract with borrow is the one. So while you are using the subtract with borrow, you will have to be careful because like in the previous addition or subtraction, if carry flag has been set, that may affect the operation of this subtraction, subtract with borrow. So always when we are going for using this subtract with borrow, we'll have to clear the carry in case if we don't want to carry on the borrow to the next operation of subtraction. Having said that, so I can go for doing it in the same file of add.asm, or else I can go for saving it with a different file name. So I'll put it as save as, so sub .asm. So now I'll have to remove this add.asm, right click, remove file. So the file goes, then right click in the source group again and add existing files to source group. So you will get, we'll have to search for this subtract.asm. So here also you keep it as ASM. So in case if it is C, so nothing will appear. ASM has to be there. So subtract, you can click and then add. So now sub.asm has been added. Then again you'll have to click translate, build and rebuild. Now I am clicking the start stop debug session. So click mov a is loaded with 5, b is loaded with 3, 5 minus 3 is 2. So that is the end of the program. Then we can replace the subb with mul also, that is multiply. So I'll put it in a separate file again. Save as mul.asm. So I'll remove this sub. You can click on and delete. So you don't have to worry whether it will get deleted. It's not deleted. I mean here when you click that particular file and press the delete button, it means that it will remove from the source group, but you will have the backup file. You don't have to worry. Then source group, click add existing files to source group, and I'll select this mul.asm. Click add, click close. So here mul, it's not a comma b, it's ab. Mul ab is the syntax. So you can't use any other registers. A and b has to be there. So you can't use a or not, a r1. Those things will not work. A and b only will work, and the workability will be in such a way like when a and b is getting multiplied, the possibly two 8-bit numbers, when you multiply you will get you may get a 16-bit number also, so in which the lower 16-bit will be in A and upper 16-bit will be in B, the result. So let us check with 5 and 3 first. 5 and 3. So you are getting F. So 5 into 3 is 15. In hexadecimal it is F. So it is showing F. So let us check with a larger number. say 23 maybe, and 12. So 23, then 12, and you can see 276. So 276 happens like a lower 8-bit appears in the accumulator, while the upper 8-bit is in the B register. In case if you want to check whether the result is correct or not, you can always use the calculator. You keep it in the hexadecimal mode, then 23 into 12. So 276. 2 is in the upper 16 bit, while 76 is in the lower 16 bit. So 276 is the result that we have got. The same program can be used for division also. So I'll change the MUL to DIV. In DIV also, you don't have an option. It has to be with A and B only. So you can't use any other registers. And in this case, A will be having the quotient and B will be having the remainder. So I'll remove the MUL and here save as. I'll put it as div.asm. So this div.asm I'll have to add, close, translate, build and rebuild. Now 23 is loaded into A and B is loaded with 12. So 23 divided by 12, you are getting 1 as the quotient and 11 as the remainder. So again you can use the calculator for checking the quotient and remainder. So 23 divided by 12, you are getting 1 as the quotient. To find out what is the remainder, what you can do is you can multiply the denominator with the quotient. So denominator with the quotient, when you multiply, what you'll get, obviously the 12. It's like a quotient is 1, so we need to put 23 minus 12, so that is 11. 11 is the remainder. So 1 is the quotient that is available in the accumulator, while 11 is the remainder. So this is again in hexadecimal. So the calculator will not give you the remainder, it gives only the quotient. So to find out the remainder, you just multiply the denominator with the quotient. So obviously you know that A is the numerator and B is the denominator. So denominator you multiply it by the quotient and subtract it from the numerator content, so you'll get the remainder. So that's it for division. So now we can do one more operation. So here we have seen the simple operation of addition, subtraction, multiplication and division. So the same addition, subtraction, multiplication and division, we can access it from the memory. So I am using the same file that whatever I have done earlier. So in which what I'll do is, instead of initializing it in the program, the numbers that is initialized over here, I'll try to obtain the values from the memory. So here I'll be using an instruction mov dptr comma hash 4500h. So dptr is data pointer. It's a 16-bit register, and in which you will have I'm moving the content 4500. 4500 happens to be the memory address. So that memory address I'll be using it for accessing the data. So in 4500 we can use whatever the memory address that we want, but when you are putting it in the board, the hardware board, we'll have to be careful what does that 4500 signify in the hardware board. So that we'll have to keep it in mind. So now mov dptr comma hash 4500, then I'll access the data from movx a comma @dptr. So here what happens is, from dptr, dptr will be having the content 4500. From 4500 the memory address, the data will be accessed into the accumulator. Then so inc dptr, so the first instruction, first value has been obtained in the accumulator, so the same value I'll move it to B register, move B comma A. Then inc dptr, I'm incrementing the dptr, so my memory pointer points to the next memory address, so that the second data that has to be added into the accumulator, I'll be obtaining it in the accumulator. So movx again A comma @dptr. So in this case you'll have to understand, you can't use any other registers over here, you are supposed to use only the accumulator. So now accumulator has the second value, well, the first value has been moved to the B register, so I can go for adding the two numbers using the add instruction. So one more thing, after adding, it's not like always my result will be in 8-bit. So in some cases my result may have a carry also, so I need to check the carry. So to check the carry, what I'll do is I'll use an instruction jnc. I'll use L1. So jnc means jump if no carry. So if after the addition operation is over, if carry is not there, then I'll be jumping from this instruction to L1. So in case if carry is there, then I'll be incrementing R not register, inc R not. R not is a register where I am putting the value of I'm incrementing by 1, so that it represents the carry. So after this is over, I am writing L1. So in L1 I'm supposed to write the instructions what I have to do after the arithmetic operation is over. Basically after this is over, I need to put the value into the memory again. So for putting the value into the memory again, what I'll do is I'll increment dptr first, so that my memory goes to the next memory address. So here in this case 4500 the first data is obtained, and 4501 that is happening with inc dptr, the second data is obtained into the accumulator. After addition 4503 I need to go, so that happens with inc dptr. So I can use the same instruction movx @dptr comma a, then again, so here the content of accumulator is the summed up value that is moved into the memory address. Then the carry is available inside the R0, so that I'll move it into accumulator now, mov a comma R0, and then inc dptr, so to go to the next memory address, then movx @dptr comma a. So my summed up value and the result has been stored into the memory. So now we'll save it as add mem address .asm. I'm storing it in a different file, so I'll remove this by using this remove file add.asm. Click yes, then right click, add existing file to source group, add mem address, add, close, and then now translate. So 0 error 0 warning, build and rebuild. So click this start stop debug session, click OK. So now we need to find out how to give the input value. So to give the input value, what we are supposed to do is click this view, memory window 1. So if it doesn't appear, you can do it again. your memory window will appear. So here you just type 0x4500. Yeah, so if it is appearing as C, it means that it is a code memory. So we are not doing it with the code memory, we are doing it with external memory. So we'll put x colon 0x4500. So in this x colon 0x4500, you type it, you give the input. So I'll give an input of say 5 and say 4. Now let us check what is happening. So you can see DPTR is loaded with the 4500 and accumulator. So it is fetching the data from 5 to the accumulator MOVX A comma DPTR, and 5 is transferred into B register. So INC DPTR, it becomes 4501. Now the 4 has to be fetched into the accumulator. So 4 has been fetched. Then JNC, obviously you will not get a carry. So, because like 5 plus 4 is 9, you will not get a carry. So it will jump that instruction and go into the INC DPTR. So DPTR becomes 4502, and you can see 9 is the result that is being stored, and INC DPTR again. So it becomes 4503. 4503 is loaded with 0 because we don't have a carry. So let us check with a different number which results in a carry. Maybe the highest number, FF and FF. So we'll run 4500 FF. Yeah, addition is over. Now the result is 1 FE. So R0 is incremented by 1. So you can see that R0 is incremented by 1. INC means increment. INC you can use it for DPTR and other registers also. Then I am incrementing the DPTR. So FE and 1. So 1 is stored in the carry. So in case if you want to check whether the result is correct or not, you can do FF plus FF. 1FE. 1FE is the answer that we have got for adding the two numbers. So the same kind of an operation can be repeated for subtraction also. Okay, let us see how does that happen. So I'll copy these instructions. Okay, so the subtract program I'll copy, because this happens to be the same. For 500 getting the first value and getting the second value happens to be the same. So I have copied that from the previous program and I have pasted mov dptr comma hash 4500 movx a comma dptr. So a I am moving it into B, and inc dptr it becomes like 4501. So the second value I am moving it into the accumulator. So in this case we'll have to be careful, because like here mov a comma hash 05 we have directly initialized, but in this case initially we have one value in A that we are moving it into B, then we are updating the content of A. So if I am going to subtract 5 minus 3, it has to happen as in the first 4500 I'll have to give 3, so that 3 comes into the B register, and in 4501 I'll have to give 5, so that 5 will come into the accumulator. That we'll have to keep it in mind. So these two I'll delete. So as we have done in the previous case in subtraction, in case if I am using a subtraction of 5 minus 3, I'll get a value as result as 2. In case if the given input value is 3 minus 5, then obviously your result will be different. So we need to check whether a borrow has happened or not. For that, the same instruction we can use JNC L1, and then I can represent that borrow in the R0 register the same way. Then L1 INC DPTR, then MOVX @DPTR comma A, then MOVA comma R0, MOV, before MOV we'll have to write INC DPTR MOVX @DPTR comma A. So whatever we have written in the previous program, I have done the same thing. So we'll save as a different file name again. In this case also save as sub mem dot asm. I'm saving it. I'll remove this by clicking this delete and then add. So sub memory address, close, translate, build and rebuild. So I'll give the value. So as I said, I'll have to give 3 and 5. So let us check individually. So 4500 from 45003 has been fetched to accumulator, then it has been transferred to B. So transferred to B, but move is like a copying. So you can see still accumulator has the value 3. So when you are typing move, it doesn't mean cut and paste, it's copying from the accumulator register to the B register. Then INCDPTR, it becomes 4501. 4501 is pointing towards this 5. So the 5 will be fetched into the accumulator. So 5 and 3 has been fetched. So subtraction is happening, subtract with borrow. So the result is 2. So you don't have a borrow, so carry will not be there. Carry flag represents both when your addition happens and when subtraction happens. When addition happens, if you get a carry flag will be set, and when during subtraction, when borrow happens, your carry flag will be set. INCDPTR, so 4502, and 2 is saved in the 4502. Then R0 value is moved into the accumulator. R0 is a 0, so 0 is saved in 4503. That's the end of the program. So in case if I'm having a different number like 3 minus 5, so 3 minus 5, in the sense I'll have to give first 5 and then 3 next. So 4500, 5 is fetched into the accumulator, then 5 is transferred to B, and the DPTR is incremented to 4501. Then 3 is fetched into the accumulator. So you can see the result is FE. 3 minus 5, it's not minus 2 as far as this hexadecimal is concerned. It will take a borrow and it will have it as FF. From the FF it will go for subtracting. So the result is FE. So when you subtract 3 minus 5, so 3, 2, 1 and 0, it is okay. Beyond 1 it will get into FF and then FE. Then your borrow flag will be set. So you can see the borrow flag, since it has been set, R0 has been incremented by 1 to represent the borrow flag. So increment DPTR and FE has been stored in 4502 and INC DPTR 4503. The borrow is represented in 4503. Okay, the same operation can be repeated for even multiplication also. So I'll copy again the same thing. I'll close. So So in this case also, as far as addition and subtraction is concerned, 5 into 2 or 2 into 5 both are same, so you don't have to worry much. Only thing is you'll have to worry when you're using subtraction and division. So because like 2 by 3 is not equivalent to 3 by 2, so that we'll have to keep it in mind. As far as addition and multiplication, a cross b is equivalent to b cross a, so we don't have to worry. So these instructions I'll delete, and you can see in this case first a will get one number, and that is transferred to b, and the second number I am obtaining it in a again, and multiply ab, and after this I can't go for checking whether the carry has been generated or not. So directly I'll put the result into the memory. So I'll use inc dptr movx @dptr comma a, then inc dptr mov b comma a. So because like a is having the lower 16 bit and b is having the higher 16 bit, so that higher 16 bit I have to take it into the accumulator so that I can print it using the movx instruction, movx @dptr comma a. So that's it. So I'll delete this, and I'll save as mul mem and I'll add this to the source group, mul mem address, add, translate, build and rebuild. So I'll type some number 5 and then 2. So let us see, 4500, first number 5 is fetched, you can see, and then 5 is transferred to b, then 2 is fetched from 4501 by incrementing the dptr, then both are multiplied. 5 into 2 is 10, that is a in hexadecimal, so it is showing a. Then movx inc dptr, so it goes to 4502. A is transferred to the memory, the result, and in the case of b you don't have anything, so 0 is transferred to that particular memory address. In case if you are having a very larger number, then we can type that one over here, 23 into 45 say. So 4500, then 23 has been fetched into the accumulator, then that is moved to b register, then 4501, 45 is being fetched into the accumulator again, then both are multiplied, so it is 96f. So you can see 6f has been transferred to the 4502, and in 4503 it will be transferring the 9. Okay, so next is we need to have the division program. So division program almost the same, so we'll replace the mul with div ab, and I'll save it as div mem .asm. I'll remove this. Div, add, close, translate, build and rebuild. So as we have done in the subtraction, the number that first you are giving should be the denominator will be giving first and then the numerator. So if I want to give 5 divided by 2, initially I'll have to give 2 and then 5, as we have discussed with the subtraction program. So you can see 4500 is loaded into DPTR, then the 2 is fetched into the accumulator, 2 is moved to the B register, then 4501. So now 5 will be fetched into the accumulator. So while it is dividing AB, it will become 5 by 2. Then so you can see 5 by 2, 2 is the quotient and 1 is the remainder. So as I've already told you, you can 5 divided by 2, you will get 2 as the quotient. So quotient and the denominator you will be multiplying, so it becomes 2. In that you will be subtracting it with the numerator. Sorry, quotient and the denominator, when it is getting multiplied, it becomes 4. So 5 minus 4 is 1. So 1 is the remainder. I think you understand. So now it goes to the next memory address 4502, and to the quotient that is being stored in 4502, and then 4503 1 is stored. So by this you can do the operation of division using the memory address. Okay, the next what we'll do is we'll try to write a program to add two 16-bit numbers to 8-bit numbers means 2 digits. Adding 2 digits with 2 digits. Now it will be 4 digits with 4 digits. So assume that this is going to be the number that we are going to add, 2 3 4 5 and 4 5 6 7. So practically we'll have to add it in such a way, like initially we'll add 45 and 67, then 23 and 45. In case if you are getting a carry, that carry should be carried over to this 23 and 45. So we'll try to have a greater number over here so that we'll get a carry. So 2 3 we'll put it as F5, and maybe this 6 7 also I'll change it to maybe A7. Okay, so these two are hexadecimal numbers. So initially it will happen as F5 plus A7. So 197. So 197 will be there, and 1 will be carried over to this 2. So 23 and 45. So 23 plus 45, 68. So 68 plus 1, it becomes 69. So let us see the result. 2 3 F5 plus 4 5 A7. So 69 9C. So whatever the result that we have obtained separately, you are obtaining it in connection with each other. So 699C. 699C is the answer that we are supposed to get. So let us write a program for that. So initially we'll write it without using the memories. MOV A comma hash. So we'll just write the first number, that is A7. So we'll start with A7, then 4 5, then F5, and then 4 5 and 2 3. MOV A comma hash A7 0A7 H, and MOV B comma hash 0F5H, then MOV R0 comma #45 hash 45H, and mov r1 comma hash 23h. Okay, now what we are supposed to do is we'll add a comma b, then so the result has to be stored somewhere because we'll be using the accumulator again. So to do that, what we'll do is we'll move the content of a to r2 register, r2 comma a. Then we don't have to check the carry because obviously when carry has happened, that I'll be taking to the next addition with the addc, that is addition with carry. So we don't have to check the carry as of now. Then I have stored the first addition result to r2 register. So the next addition result I need to take, so that I'll take it using mov v a comma r naught, and then add c a comma r1. So 45 I am bringing it to the accumulator, that I am directly adding with 23. Then here, in case if you still have a carry, that you can check jnc l1, and then here inc, I'll keep r3 for the next result, so r4 I'll use it for carry, inc r4. Then L1. So here I'll end the program because before ending the program I need to store the value of a in the higher 16-bit. So mov r3 comma a, then so l colon s jump l. So end of the program. So I'll save it as add 16.asm. So the program is has been typed. Now I'll have to add it to the source group. Add existing files to source group, add 16, add, so translate, build and rebuild. Now let us check the results. So A7 is loaded into the accumulator, then F5 is loaded into the B register, then R0 with 45 and R1 with 23. Add AB, so 9C. In case if you want to check whether the carry has been represented, you can always click this plus button of PSW. PSW is program status word, so in which you will have this CY. CY represents the carry. So here you can see a carry has been represented, so which means that carry has happened. That's what we have checked with the calculator earlier. So carry has happened, that has been represented in the carry flag. Then mov r2 comma a, the result I am moving it into r2, the lower 8-bit I am moving it into the r2 register. Then I am moving the r0 content 45 to the accumulator, and I am adding 45 with 23, so it's 69, and it doesn't have a carry. You can see that when this addition is over, the carry flag has been made as 0. So this R4 has been skipped, so the value of the result has been will be stored into the R3 register. 699C is the result. So that is the result that we are supposed to get, 699C. In case if I wish to do it with the memory, what I should do? So in memory we'll be trying to give it in a sequence. So this will remove, then put mov dptr comma hash 4500h, then mov x a comma at the rate dptr, then inc dptr. So in this case we'll give the input in such a way as starting from this one. We'll give the A7 first, then 45 next, then F5 next, and 23 next. So after giving A7, we'll increment the DPTR to point to this F5. Then we'll add these two together. Then we'll make the pointer to work point to this 45, and we'll add these two numbers together. So that while giving the input will not be confused, because when you're using the memory, we are prone to give the numbers according to some pattern. So if the pattern is differing, then we may get confused. So while giving into the memory, we'll give it as A745 F5 and 23. This will be the sequence that we'll be giving. So here what I should do is I'll have to put 2 times incdptr mov x a comma at the rate dptr. So obviously we'll be obtaining a7 and f5. So a7 and f5 mov b comma a, so that the first value is stored into the b, and 2 times I have incremented. So now the value has been fetched into the accumulator. So addition happens here. Then after adding, what I'll do is I'll store the result. If I want, I can store the result. So to store the result, I can initialize the dptr again with hash 45. So you can see here 4500, 4501, 2, 3. So from 4 I'll print the result 4504h. So movx at the rate dptr comma a, so that the result is stored into the 4504, that is the lower 8-bit result as stored into the dptr. Then we are supposed to go for the next value. So next value is available in 4501 and 4503. So we'll reinitialize the dptr mov dptr comma hash 4501h, then mov x a comma at the rate dptr and mov a comma b, then b comma a, then inc dptr, and because the next input is available in 4503, so 2 times you are supposed to increment the dptr. So mov x a comma at the rate dptr. Okay, so now I'll put add c a comma b, j and c. So in the similar way, jump if no carry. So in case if carry is happening, it will happen in not R4 register. Will R4 can be done. R4 can be there, no problem. Then here what I should do is I'll have to reinitialize the dptr. So mov dptr comma 4505, because this will have the upper 8-bit result. So that is available in the accumulator. So directly we can use movx at the rate dptr comma a and inc dptr to go to 4506. So 4506 will be having the carry. So mov r4 comma a comma r4 movx at the rate dptr comma a. That's the end of the program. Now let us run it. Translate. So one error is there in the 19th line. So here mov dptr comma hash 4505h 0 error 0 warning. Translate, build and rebuild. So as I've already told you, we'll be giving it in the sequence A745 F523 A745. So here A745 F523 A745 F523 has been given as input. Now let us see how the program functions. So first 4500 is initialized, then A7 is fetched, then that is moved to B, then 2 times incremented the dptr, then A5 is fetched, so A5 and A7 is added, so 9C. So that I am moving it into the 4504. So 9C has been moved. A part of the result has been obtained. Then I am reinitializing the dptr to 4501. So the second value is 45 will be fetched, and then that is transferred to B register. Increment dptr 2 times 4503. So 23 will be fetched. 23 and 45 is added with the carry. Then if carry has been generated, that is checked, so carry is not there. So in 4505 the result is transferred, the lower byte result is transferred, that is 69. 699C is the result. And then since we have written the code for putting the carry also, that is getting executed, but that is 0 in this case. So this is the way you can write a program with the memory for 16-bit addition. 16-bit addition. Okay, now we'll go for 16-bit subtraction. So in 16-bit subtraction, we'll assume that these are the numbers that we are going to subtract. 4529 minus 2373. So 29 and 73 has to be subtracted first, and in case if it gets a borrow, so in this case it will get a borrow, that will be carried over to this one. So the result will the borrow whatever that has been carried over here will be subtracted again. So you can see 29 minus 73. So here it is all the values that is resultant will be showing as FFFF. So this we can discard, only the B6 is the one that we are concerned with. So here it will be B6 while the borrow will be set. So 4523, 45 minus 23, 45 minus 23 minus 1. So 21 should be the result. So here 4529 minus 2373. So 21 B6 is should be the result that has to be obtained. So let us program the Keil for this. So we'll use the same pattern. So but we'll put it as a different name. SUB 16 dot asm and save. So we'll remove this, add 16.asm and add this sub 16.asm. Add. Then we need to do certain changes. So we'll directly get into the mode of getting the values from the memory address itself. So in case if you want to do it with the registers, obviously that you can do in whatever the pattern that you feel that is comfortable. So we'll keep this as the base, and in this we'll try to manipulate the values. So here so the as we have done in the previous case, 73, 23, 29, 45 is going to be the number sequence that we are going to give as an input to the memory. 73, 23, 29 and 45. So 29 and 73 should be obtained first and it should be subtracted. So in this case addition is different, where a plus b is equal to b plus a, but a minus b is not equivalent to b minus a. So 29 minus 73 has to be given in a particular sequence. So in this case 73, 23, 29 and 45 will be feeding in. So whatever the fed in value, initial value 73 will be obtained into the B register, and 29 will be obtained in the A register. So A register, so A minus B will happen. So simply I'll change this add to SUBB. So as I've already mentioned here, before the SUBB we are supposed to use CLR-C, clear carry, so that in case if previous operation has resulted in carry, that doesn't affect this first subtraction, because you don't have a subtraction without borrow, but addition without carry is there and addition with carry is there, but subtraction there is only one instruction, that is subtraction with borrow. So I am using this CLR-C. So A minus B will happen. So you can see first initially in 4500 we'll be having the value 73, and 4501 will be having 23, and 4502 will be having 29. So 4500 73 will be there, 73 will go into B register, and 23 in 4501 and 29 in 4502. So 4502 has come will come after the 2 INC DPTR, and possibly the 29 will get into the accumulator. So both will be subtracted initially. Then I'll reinitialize the DPTR with 4504, so that the result is stored in the A. So the result is like the last 8-bit result is stored in the 4504. Then I am reinitializing the DPTR with 4501. So 4501 will be having 23 and 4503 will be having 45. So 23 is obtained in the B register, while I'll be incrementing twice. So 45 will be obtained in the accumulator. So A minus B will happen. So 45 minus 23 will happen. So here I'll have to put again this SUBB. So while this subtraction happens, the accumulator minus B register will happen, and in this case again, in case if you want to check whether borrow is there, that also can be checked using the same instruction JNC. So the result, the higher order result is stored in 4505, and in case if borrow is there, that is stored in 4506. So let us see the operation. Translate, build and rebuild. As I have mentioned earlier, we'll give the input as 73232945. 73232945. 73232945 has been given as an input, and we'll write the result also. 4529 minus 2373, 2156 is the result. 56, sorry, it should be in hexadecimal. 4529 minus 2373, 21B6 is the result that we are supposed to get. 21B6. Okay, now let us check. So 4500, 73 is fetched, then that is moved to B register, then 29 will be fetched from 4502, and that is available in A register, and carry is cleared, and then 29 minus 73 happens, so B6, so that is stored in 4504, then 4501 DPTR is initialized, and then the result, the value 23 is fetched, and then 2 times INC DPTR, so 4502, so the value 4503, so the value 45 is fetched into the accumulator, and 45 minus 23 happens, so it is 21 with the subtraction of the borrow, and INC R4, there is no carry, so it will jump to the instruction INC R4. Again I am reinitializing the DPTR with 4505, and the value 21 is stored in 4505, and 4506 0 will be stored, that is the borrow flag. So 21B6 is the result. So the result we have obtained as we have calculated using the calculator. So this is for subtraction. Okay, now we'll discuss about how to write program for adding two 16-bit numbers. So here in this case I have made it as getting the input into the register itself, because like in this case the program is becoming much bigger, so we'll start with this one and we'll try to convert this one to the we'll add the things that is related with accessing the memory. So here in this case you can see I have initialized the number, so the number happens to be like this one, 5152 multiplied by 4532. So 5152 multiplied by 4532. So so here 52 and 32 are the lower digits or lower 8-bit numbers. So here the basic idea of this program is repeated addition. So 5152, it has to be added to itself 4532 times. As far as this ARM processor is concerned, it has only 8-bit multiplication instruction. For 16-bit multiplication, we don't have a separate instruction. So what we will do is we'll do the repetitive 16-bit addition of 5152 with itself as 5152. So you can see here MOV A comma R3. So the R3, the lowest 2 digits, I am moving it into the accumulator. Then MOV B comma R4. So here the R4 register I'll be using it as a resultant register, R4 and R5, and in addition to that I'll use DPTR also, because like when you multiply two 16-bit numbers, you are prone to get a 32-bit number, so you need a totally 32-bit location. So R4, R5 and DPL and DPH, that is the parts of DPTR. DPL means data pointer lower bit and lower byte, and DPH is a data pointer higher byte. So totally you will get 32 bit output. So here this R4 is the lower 8-bit. So here what I'm doing is I am initially R4 doesn't have anything, so I am just putting that to B, then add A and B. So that is like I'm adding 52 to 0. So that is the if 52 is multiplied by 1, it will result in 52. So that gives this result as 52 over here. Then after the addition is over, the value of E I'm updating into the R4 register. Then I am moving the value of 51 into A register. So 51 is the upper bit, so that I am moving it into the A register, and R5 I am using it for the upper bit resultant register. So that R5 also I am having it added to the B, moving it into the B. R5 doesn't have anything, 0 initially. So add C, add with carry A comma B. So the B is 0, that is added with the your accumulator. That accumulator happens to have 51. 51 is added with 0, so 51 will be the result. So that I am updating into R5. Then in case if I'm having the carry, so I'll be representing in dptr. So here I have used this dptr because as I've already told you, this is 16-bit multiplication. You are supposed to get 32-bit. So to get a 32-bit, this dptr happens to be giving a consistent result, because other registers are all 8-bit registers, but the 16-bit register you can manipulate it using this INC operation. So that's it. So this operation will happen again and again until 4532 goes to 0. So 4532 we'll have to decrement it. So now once we have added 5251, and subsequently one other time 5251 will be added with 5251, so it will get accumulated. So the accumulated results will be available in R4 and R5, and when the carry is obtained, the carry will be represented in dptr register. So this 4532 has to be decremented. So there is no decrement instruction for 16-bit registers. So what we have to do is we'll have to include the 16-bit subtraction that we have already done, so that we'll subtract these two numbers, and when both the values goes to 0, we'll stop the addition process. Until then we'll be adding it. So that is the process that is going on over here. So what we are doing is we are clearing the C, so that the previous operations carry doesn't affect this subtraction. So now I am moving A with R1, so 32 moves in, and I'm subtracting it with 1. Then I'm moving R1 with the A, that is like I'm updating the value of R1. Then I'm moving A with R0. R0 is the higher byte of the the input that we have, one of the input. So that I am subtracting it with 0. So subtract with borrow with 0. So we can understand 4532 has to be subtracted by 1, not 101. So if you are putting 1, it means that it is subtracted as 101. So here 01, that is 0001. So in case if borrow is there, that borrow will be subtracted over here. Otherwise only 0 will be subtracted. So that is updated again and again over here. Then I am moving the content of R1 into A. R1 is the lower byte, and R0 is the upper byte. So both I am doing the OR operation. So in OR operation, in case if any one of the bit is available, the result will be some it will have some number. So if it is resulting in 0, that means that both the registers has gone to 0. So when that is happening, I'll come out of the loop. Until then I'll be repeating the loop 1 again and again. This goes again and again to give the multiplied output. So now let us see what is the output that we are getting. So here you can see 5152 multiplied by 4532, we are getting 15FA FC04. So you can see 5152 multiplied by 4532, 15FA FC04. Let us see, translate, build and rebuild. then start stop debug session. So in the start stop debug session, what I'll do is, instead of going step by step, because it will take a lot of time to make this 4532 to go to 0, so I'll directly press this run button and press the stop button. So I'm getting the answer now. So as I said, R5 and R4 happens to be the output resultant value. So this is like a lower 16 bit, while upper 16 bit is in DPTR. So you can see 15FA and uh, FC04 is the result that we have got for 16-bit multiplication. So in case if you want to make this happen with the memory, obviously you can replace this instructions with MOV DPTR. Yeah, you can use this DPTR over here. Yeah, in case if you want to do with the memory address, what you'll have to do is, we'll have to release this DPTR and we'll have to do a 16-bit addition again over here. So again the program will become lengthier in that case. So we'll stop with this one itself, and now we'll get into the 16-bit division. So this is 16-bit division, in which you can see we are subtracting the number A541, dividing the number A541 divided by A0C. So in this case, as we have done in the previous cases, we are initializing the number with R0, R1, R2 and R3, and but in the previous case we had a different fashion. So here the fashion will be in this way: R3 is the upper byte, that is A541 numerator, while 0A 0C is the denominator. So usually for a division to happen, we need to check whether the numerator is lesser than the denominator. If numerator is lesser than the denominator, we'll have to come out of the division process. So it will be meaningless. So your numerator will be the remainder and quotient will be 0. So in that case, so we need to check whether the numerator is lesser than the denominator. To do that, first what you will do is, we'll check whether the A5 is lesser than 0A. So in this case it is not less, but in general case, when you are giving a general input, so we need to check that one too. So for that operation we have this particular set of instructions. You can see MOV A R3, I am moving the content A5 into the accumulator, and subtract with borrow A R1. So this is the upper byte of the numerator, and this is the upper byte of the denominator. Both I am subtracting to compare whether this numerator upper byte is lesser than the denominator upper byte. If it is lesser, obviously the whole numerator is going to be lesser than the denominator, then I'll have to stop. So that's the reason I am subtracting A R1, and I am checking the carry. If carry is set, which means that the program, the numerator is lesser than denominator, so I'll come to the halt. So further I will not proceed. In case if in this case it is A5 is greater than the 0A, so it goes to the next instruction. So I am checking whether the values are equivalent. So in case numerator both the values are equivalent, so there are chances like the numerator lower byte and denominator lower byte also we need to check. So there are chances like in the numerator lower byte can be lesser than the denominator. So in that case we need to check whether that is happening. So to check that, I am taking the I mean, you can see over here I'm clearing and I'm taking the R2, that is numerator lower byte 41 I'm taking into A, and R0 is there, so that also I am checking whether both are I mean lesser, I mean numerator is greater than the denominator. I mean, this condition happens only when this one is I mean numerator is 0. I mean numerator 0 in the sense numerator and denominators upper bytes are equivalent, then only this condition goes into picture. Otherwise if it is j and z will go into the loop. So if it is not equal, then itself will go into the loop, so we will not worry about it. So in case if the lower byte in the lower byte of numerator and denominator, if both are I mean numerator is lesser than the denominator, then also will halt. So that's the reason JC halt has been represented. MOV A comma R2 41 has been stored into accumulator, and SUBB A comma R0. So 0C is subtracted, so and checked whether the numerator's lower byte is lesser than denominator lower byte. So if it is lesser, then I will come to the halt, so we will not do the division process. So this is the first check that we'll have to do before getting into the division process. So after doing this checking, then we'll have to enter into this repeated subtraction, repeated 16-bit subtraction of the numbers. So so A541 will be subtracted with 0A 0C. So here first I will have to clear the carry, then move A comma R2. So the lower byte of the numerator is moved into the accumulator, then that is subtracted with lower byte of the denominator 0C. Then the result is updated into R2 itself. Then MOV A comma R3. So R3 is moved into the accumulator, that is the upper byte of the numerator, and R1 is upper byte of the denominator is moved into that is R1, that is not moved, but is being subtracted in SUBB A comma. So the result is moved into the R3 again, and INC DPTR keeps the count of how many times this subtraction is happening. Once the subtraction has happened, the DPTR will be incremented by 1, then it goes into loop again, and again it checks whether the numerator has gone lesser than the denominator, and the denominator is lower byte is lesser than the numerator is less, lower byte is lesser than the denominator's lower byte. In case if the numerators higher byte, both of the numerators higher byte and denominators higher bytes are same, then denominator will be checked. Then in case if any one of these things happens, it comes to the halt. Otherwise again the subtraction process will go on. So the subtraction process will go on until your numerator becomes lesser than the denominator, and when it becomes lesser than the denominator, then the division process will stop, and whatever the DPTR content has, that happens to be the quotient, and the value that is resulting in R2 and R3 will be the quotient. So now let us check the process. So as I have done earlier, in this case also we can go by step by step, because like it doesn't happen so many times, because it's like decaying. Division is decaying while multiplication is the number of counts will be very high. So you can see now C is loaded into R0, A is loaded into R1, and 41 is loaded into R2, and A5 is loaded into R3. Then carry is cleared, then MOV A comma R3, that is the higher byte of the numerator is moved into accumulator, and that is checked with higher byte of the denominator. So subtracted, so obviously you will not get a carry, so you will not get a 0 also, so it goes into the subtraction process. R2 is content, that is 41 is moved into the accumulator, then subtract it with R0, so 35 is updated into R2, then the this is lower byte, then the upper byte, that is A5, is moved into the uh, accumulator, then it is subtracted with the R1, then that is A, then again it is updated into the R3, whatever the subtracted value, that is updated into the R3, then again the process repeats again. You can see it comes to the beginning for checking again. So A and the R3 content is moved, so each and every time R3 and R2 will be updated, and so doesn't happen, and there is no zero, so it comes over here again. The same subtraction process goes on. So so you can see each and every time when the subtraction is over, this dptr is getting incremented. Now it has become 3, so subsequently 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and 10. Okay, now you can see the R3 content has become 4 while R1 content is A. So now we can see clearly the numerator has numerator's upper byte has gone lesser than the denominator's upper byte, higher byte. So the program will jump with the JC halt itself. It will jump to the last instruction. So the program is over. So your quotient is 10, that is dptr, and the remainder is 481. So to check that, you can always use this calculator. So as I've already told you, so A5 41 divided by A0 C. So 10 is the quotient that has been obtained. To find the remainder, what you will do is, as I have already told you, the quotient should be multiplied by the denominator, that is A0C. 10 into A0C. So A0C0 is the value. So A541 minus A0C0 we'll have to subtract. A541 A541 minus A0C0. 481 is the remainder. You can see R3 and R2, it happens to give you the value 481. So this is your remainder. So this is the way in which you can program the 16-bit division. Thank you.